So now let's take a look at how we can combine capacitors in circuits, like the diagram shown over here, to help smooth these currents. Okay, so if I go back over here, okay, the whole point of capacitors is to smooth those currents. And like I said, if I only had one small capacitor, I might not be able to prolong that current, okay, when the AC current goes down too low. So often what we have to do is we have to put capacitors in series or in parallel in a circuit to help us store enough charge so that we can prolong how long that charge leaks into the circuit to smooth it out. So again, multiple capacitors can be arranged in a circuit to help smooth AC currents. So the goal of the next few videos is to analyze two different formations. I can connect capacitors in parallel, okay, and we can look at how that affects the current smoothing, or I can connect the capacitors in series, all right? And we're gonna play around with these relationships and learn how to do some calculations with them to figure out how we can calculate, for example, the charge stored on each capacitor, the total charge stored, or whatnot, okay? So ideally, what these capacitors are really doing is they're making one large capacitor. Whether we did it in series or in parallel, we're making a larger capacitor out of this to then leak charge into the circuit, okay? So we're gonna start our story with just looking at parallel circuits, okay? So like we did with resistors, parallel resistors, there's some similarities, but there are some fundamental differences in the formulas. And hopefully by the end of this, you're going to figure out, so that you have that light bulb in your brain, that you realize that there is a little bit of a difference in the formula for capacitance than resistance. But here I have an example of two capacitors linked in parallel, okay? And just like in resistors, when you have parallel resistors, we distill them into a total resistance, okay? So these capacitors are in parallel, but I can think of them as one giant capacitor that is composed of two parallel capacitors. Okay, so it's a battery with multiple cells, for example. Okay, so how do we treat this? Well, whenever you have capacitors in parallel, the total capacitance is going to be the sum of the individual components. Okay, so the capacitance of that capacitor plus the capacitance of that capacitor. And if I had more in parallel, I would add them together. So C total is equal to C1 plus C2 plus ... okay? Then I can calculate the total capacitance. Once I have the total capacitance of that component, I can then go and solve for the Q total. And Q total is going to be the sum of the charge on each capacitor added together. So you can think of a parallel capacitor being batteries connected in parallel, okay? Or maybe, but they work together to store charge, okay? So the more I have in parallel, the more charge I'm storing together, okay? So let's take a look at a practical example. Here I have a circuit with a 10-volt battery attached to two capacitors that are connected in parallel, all right? So one of the questions I want to ask is, well, what's the total capacitance in this circuit? Well, according to the rule up here, the total capacitance is C1 plus C2. So 1 farad plus 2 farads is 3 farads. So the total capacitance of that element is 3 farads. So how can I solve for the total charge stored on these capacitors? Well, the total charge is equal to the charge on this capacitor plus the charge on that capacitor. Okay, to find that, 10 volts is being applied across this, and 10 volts, remember that's the rules of parallel circuits. They're being applied to both of these. So 10 volts times the capacitance will give me charge, according to the formula C is equal to Q over V, okay? So capacitance times voltage gives me charge. 1 farad times 10, that's 10 coulombs, plus 20 coulombs, my total is 30 coulombs. Alternatively, I could find out what the total capacitance is and then multiply that by voltage. So the total capacitance is 1 farad plus 2 farad times 10 gives me also 30 coulombs. And that's how we play with that, okay? So once I know the total amount of charge, I can then, in the next series, I'll show you how you can apply it to a formula to figure out the time it takes for that charge to leak out. Okay, that's a little bit more complicated, but we'll get there. So in the next video, now we're, instead of connecting capacitors in parallel, we're going to look at capacitors in series.